We have just seen that the double-slit experiment gives us quite different results for bullets and waves. When we perform it with the particles, like bullets, the resulting graph with the both slits opened is just the sum of the graphs with each slit opened separately. When we perform this experiment with the waves, there's no particles to count. So instead of the particles, we measure the characteristic of the wave called intensity. And the resulting graph for this intensity with the both slits opened is not at all the sum of the intensities with the slits opened separately. So this double-slit experiment appears to be a good instrument for us if we want to distinguish particles from waves. If we are not sure if something is a particle or a wave, we can test it with this set. First, we perform the experiment with the slits opened separately, draw the graphs, and then see if the graph for the both slits opened appears to be the sum of the graphs for the separate slits. If not, then we can conclude that we have an interference, and the thing we examine exhibits the wave-like behavior. And as you can guess from the name of this episode, the things we are going to test are photons and electrons. Let's start with photons. Humanity tries to research the matter of light for hundreds of years. Newton, for example, believed that light consists of particles. When this light particle hits the surface of glass, it can go through it or it can reflect. However, Newton could not explain why these particles reflect only from the surface, and we never see them reflected from the inside matter of the glass. Actually, they do reflect from the inside matter of the glass. There were other inexplicable things concerning multiple reflections from multiple surfaces, etc. These problems were generally solved with the wave theory. In the beginning of the 19th century, British scientist Thomas Young presented to the Royal Society the results of his nowadays famous work, the double-slit experiment with light. Young's experiment showed that light has an interference on two narrow slits. It was a very strong argument in favor of the wave nature of light, thus leading to development of wave theory of light, then to electromagnetic waves, and finally to Maxwell's equations. Everything was going nice and smoothly with the wave theory until in 1905 German physicist Albert Einstein researched the photoelectric effect, showing that light actually consists of indivisible packets he called photons. This raised a lot of questions. First of all, how is it possible that particles of light, photons, can have an interference on the double-slit set? Because after the Einstein's result, this interference did not disappear. We can still observe it. Maybe these particles interact with each other, like the water molecules do in the sea. Maybe if we could arrange the experiment where we fire photons one by one towards the two slits, there will be no interference, and we will see the same picture as with the bullets. Let's see. Okay. We have again the same set as we had with the bullets. But instead of machine gun, we now have the source of photons, which can fire photons one by one. For example, one per minute. Now instead of just closing the slits, we are going to act smarter and place the photodetectors after them. A photodetector is a thing that can detect photons. When a photon hits a detector, we hear a loud click. The loudness of that click is proportional to the energy of the photon. All the photons in our set will have approximately the same energy. So if we hear the click, which is definitely less loud than the others, we might conclude that the detector was only partly hit. So it detects only a part of the photon. Now, the first thing for us to discover is that there is no such thing as partial hit. If we hear a click, it is always of the same loudness. The second thing we can observe is that both the detectors are never hit simultaneously. If the photon reaches the detectors, it only reaches one of them, and never both. So the photons really resemble bullets, not waves. For a wave, it would be very natural to hit both detectors, transmitting only the part of its energy to each of them. Photons are bullets. Okay. Now, if they are bullets, we are going to count them as we did with bullets. We remove the detectors, and instead of the sandbox we used for bullets, we place the second screen, which is able to detect photons with all its surface. When this screen detects the photon, instead of a click, it gives us a flash, exactly at the place where the photon arrived. Again, we count the flashes and we draw the graph. And we do it at first with only one open slit. Here on the slide you observe the graphs for the left and the right slits being opened separately. They are pretty much the same as we saw for the bullets and the waves. No surprise up to this point. Now, can we predict what we will obtain for the situation with the two open slits? Well, it would be very natural to assume that the resulting graph is just the sum of the graphs for the different slits. Since the photons are like the bullets, the result must be the same as we had with the bullets, which was no interference. But it's not what we have. If we send enough photons, one by one, we will observe the interference picture. Pretty much the same as we have seen with waves, and very much the same as predicted by the wave description of light and Maxwell's equations. Maxwell's equations predict this picture for the wave intensity, which is, as we remember, the power per unit area. But it is exactly what we count. Photons transmit small equal pieces of energy. They actually are the small equal pieces of energy. So when we count photons, which hit the particular unit of surface during some unit of time, we really calculate the energy which was transmitted to that surface during that unit of time, which is intensity. So, however, the separate photons act like particles. The overall picture has the wave description, even when the photons are fired once in a minute, so we can be very much sure that they don't interact with each other.